Good day, students. Today I just want to look at some characteristic organic reactions for ASA level chemistry, syllabus code 9701. This is section 13.2, an introduction to the basic foundations of organic reactions. I'm going to look at some terms such as saturated, unsaturated, homolytic, and heterolytic fission, as well as nucleophile and electrophile. I suppose if I cover those terms, you'll be in a position to have a foundation for your organic chemistry reaction. Okay, saturated and unsaturated, this one is a continuation from your O-level studies, okay? Saturated, okay, and then on this column, I'm going to have unsaturated, okay? Now, from your O-level, we are going to assume that you have some background information as to what is a saturated molecule. Okay, now when you are looking at saturated molecules, you are looking at those molecules in which carbon has the maximum bonds around it, your alkanes. Okay, these are saturated molecules. Okay, so this is 1, 2, 3. Okay, this is propane. So your alkane family, the alkane family consists of saturated molecules. If we can just extend and link to what we covered in our previous sessions, saturated molecules, okay, I suppose you still remember that these ones, they show us sp3 hybridization, okay? They show us sp3 hybridization, okay? And we can also extend our knowledge here, and we saw this is tetrahedral and the bond angle is usually 109.5. Okay, so this is our saturated molecules. They are saturated, okay? And because they are saturated, it means carbon contains the maximum number of atoms around it. So if you want your alkanes to react besides combustion reactions, okay, you have to, they undergo substitution, okay? Substitution, right? So you have to replace hydrogen atom, okay, by another atom such as a halogen atom in your free radical substitution reaction. They are saturated and they undergo substitution. Saturated, substitution. I suppose that should be fairly easy to remember. Unsaturated, okay, you are looking at molecules such as in the alkene family, okay, unsaturated, all right. You see, carbon is in a position to form 4 bonds around it, okay, 4 atoms around it. But we have 2 here in the double bond, so we can break this double bond and accommodate more atoms, okay. So the double bonds, okay, like the alkene families, okay, like this one, which is ethene, right? It's an unsaturated molecule, and if I can also just do what I did on the other side, these ones, they tend to show us what? sp2, okay, hybridization. All your alkene molecules, they tend to show us sp2 hybridization, and if you look at the bond angle there, it's going to be 120, okay, 120 degrees for the bond angle there. And also, because they are unsaturated, okay, we are saying carbon is still in a position to accommodate, okay, more atoms around it. We don't have to perform substitution, all right, because it's unsaturated. It's not yet reached, it has not yet reached its maximum number of atoms around it. So we still have room for adding more atoms, okay? So because we still have rooms for adding more atoms, these molecules, they undergo what we call addition reactions, okay? So your alkenes, remember, they undergo addition reactions, but your alkanes, they undergo substitution reactions, okay? Right, so basically, this was covered even at your IGCSE study for chemistry. We're just adding a bit more flesh to introduce you all to our AS chemistry. Okay, so I have covered unsaturated and saturated. So today, my studies will be using a comparative approach, okay, so that you are in a position to compare. So I'm not going to remove this line because I'm going to be using a comparative approach. Now I am going to the next one. It says homolytic fission, okay, homolytic fission, and here it says heterolytic fission. All right. So again, we are going to compare between these two terms, homolytic fission and heterolytic fission. Right. The word homo means the same. All right. Homogeneous mixture. So when you're saying homolytic fission, we are breaking a bond where the atoms that were involved in the formation of that covalent bond are exactly similar. Okay. For instance, let's look at bromine. Okay. And bromine, okay? That's a halogen molecule, bromine, okay, molecule. When we are having free radical substitution, for instance, okay, in the presence of UV, all right, this bond can be broken. And because these atoms have similar electronegativity values, you are going to find out that the shared pair of electrons, one electron will go to that bromine atom and the other electron will go to that bromine atom. That's why I'm using half arrow. Okay, and one bromine atom ends up with one electron, the other bromine atom will end up with one electron. What do we produce? We are going to produce bromine, okay, with one electron plus bromine with one electron there. Okay, and what are we saying here? We have what we call free radicals. Okay, free radicals. These are highly reactive species because these electrons would want to pair up, okay, and form a bond. So we have free radicals that are produced as a result of homolytic fission. Let's move over to the other side of the table. We now have heterolytic fission. Hetero means different, such as heterogeneous, okay? Right, so we are going to use this example, HBr, okay? Now there's a difference. These two atoms are different. That's why we are saying heterolytic fission, right? So this type of bond, okay, when bond fission happens, all the electrons are going to move to the bromine, okay? So you're going to find out your bromine will actually have a partial negative charge and this one will have a partial positive charge, okay? You're going to be seeing these partial positive, partial negative as I cover organic chemistry mechanisms, okay? And then what will happen as we carry out bond fission here? We are going to have this one becomes positive and that one bromine or our bromide ion is also formed there, okay? And we are going to produce ions, okay? The difference is in heterolytic fission, we generate ions. In homolytic fission, we generate free radicals. That's the difference, okay? All right. And you should understand the fact that in our homolytic fission, our atoms were exactly the same. And as a result, the electrons were shared equally, okay? This is a non-polar molecule, okay, because the electronegativities are exactly similar, but this one is a polar molecule because bromine is more electronegative than hydrogen. So when you break that bond, you produce free ions, okay? So that's the second comparative study that we are supposed to look at, okay? The last comparative study that I'm going to discuss today is nucleophile and electrophile, okay? Nucleophile and electrophile. You are expected to be in a position to have a simple definition for what is the difference between nucleophile and electrophile. Let me start here with electrophile, okay? Electrophile, and then I move on to this side and I'm going to discuss nucleophile, okay? Right, when you look at an electrophile, you are looking at a species that is attracted, okay? It's attracted. It is attracted to electron-rich, okay, regions of organic molecules. That is an electrophile, okay? Like you can have a double bond, okay? This one is an electron-rich region, okay, of an organic molecule. So electrophiles will be attracted to such regions, okay? Because of this simple rule of saying unlike charges attract. So my electrophile in most cases is going to be positively charged, okay? It must be positively charged. My electrophile must be positively charged, okay? So this is the story that we can have on this side. Let's switch over to nucleophiles, okay? These ones are attracted to positive carbon senders. Positive carbon senders, okay? Positive carbon senders. You're going to find out that as we develop our concepts in organic chemistry, we're also going to call them carbocations, okay? But for now, let's just say positive carbon senders, okay? And these ones are usually negatively charged, okay? Usually negatively charged or having lone pairs of electrons. These are the conditions for a species to behave as a nucleophile, okay? So you can actually have your atoms such as Cn minus, your cyanide, okay? It's negatively charged, so it can be a nucleophile. You can have your hydroxyl, okay? Negatively charged, also having lone pairs of electrons, very good nucleophile, okay? You can even have molecules such as water, okay? Water with its two lone pairs, it can behave as a very good nucleophile. I can also talk of ammonia, okay? Ammonia, you still remember? Ammonia has a lone pair of electrons. So, negatively charged, lone pair of electrons, okay? Negatively charged, lone pair of electrons, lone pair of electrons. So any species that has a lone pair of electrons will be attracted, obviously, to a positive carbon sender because unlike charges will attract, okay? If something is positively charged, it's going to be attracted to an electron-rich region of an organic molecule, okay? I thought I should just describe these terms so that you have a fair understanding of organic chemistry reactions. What's now left under this section is for us to look at what is under section 2, understand and use the following terminology associated with the type of organic mechanisms. So in my next session, I'm going to touch on electrophilic addition. I may also touch on nucleophilic substitution, okay? Because we now have an understanding of an electrophile and a nucleophile, we should be now in a position to discuss electrophilic addition and nucleophilic substitution. This was our session today. I hope you have managed to remind yourselves of some of these basic definitions, and then you should be in a position now to carry over this information to the next discussion when we are going to look at the types of organic chemical reactions. Thank you for listening to this session. Remember, if you are benefiting from this series of videos on my YouTube channel, just remember to subscribe, and also just indicate by liking, share with your friends, because I normally use very simple explanations, very simplified language so that I bring chemistry to your doorstep. Please remember to like these videos, and also just check there are a couple of videos there. You never know, you might actually get some explanations that will help you in your approach to exams, okay? Videos that I normally upload are usually as a result of students asking these questions. Some students are preparing already for the May-June exam sessions, which are fast approaching. I'll see you in my next session when I will now delve deeper into the types of organic chemistry reactions, whereby I'll be talking of electrophilic addition reaction and the nucleophilic substitution reaction. Thank you. I'll see you in my next video.